Welcome to Ready to Derive. In this video, we'll be learning about the method of U-substitution to help us work out indefinite integrals. And that's integrals of what appear to be very complicated functions. Now, why are they complicated? Because they involve composition of functions. So before we begin, let's just review a very important result, is that if we have a composite function like this, and we take the derivative with respect to x, then by the chain rule, we should get this. And all U-substitution is doing is helping us get back in the reverse direction. Now, the reverse direction would be taking the integral, and because integration, differentiation are technically inverses, we should be able to get back to the original composite function. Almost. We mustn't get the plus c. So the method of U-substitution will allow us to work out much more complicated integrals than we've been accustomed to doing. So without further ado, let's begin. So let's take stock of what we can integrate up to this lesson. So we know that if we were asked for the integral of cosine x dx, we just want the antiderivative, and the answer is sine of x plus c. So what we're being introduced to in this lesson is, what if it's not so simple? So what if we want the antiderivative of cosine of 2x? So we have a function 2x within a function cosine. Well, sort of thinking reasonably about it, logically, probably it should be something of the form sine 2x plus c. Otherwise, how are you going to get cosine 2x when you take the derivative? And the way we check this is we say, well, let's double back. So let's take the derivative of what we think the answer is. And the derivative of sine 2x is cosine 2x, and by the chain rule, they'd have to be times 2, and the derivative of a constant is 0. So we have a little extra here. See, we have a 2 here, which doesn't appear in the original problem. So for this statement to be true, I would need a 2 here, because then I could say that the integral, let's look over here, if I take the integral of 2 cosine 2x, that will indeed get me back to sine of 2x plus c. With the same sort of reasoning, we have another composition of functions. We have x squared within the function cosine. Again, thinking sort of logically, it should look something like this, sine of x squared plus a constant. But let's take the derivative just to check. So we have the derivative of sine of x squared will indeed be cosine of x squared. So check, we've got that. But by the chain rule, we will have a 2x there. So in fact, we couldn't even work out that integral unless we had a 2x in front of here. So we are looking for very specific situations. What are we looking for? We are looking for a composite function. The techniques we'll learn in this lesson, we need to have a presence of a composite function here. So we have a composition, a function within a function, but then a very crucial element in order to be able to do U-substitution is that you see some form of the derivative of the inside function. So g is the inside function, g prime x is the derivative, and it kind of has to be hanging out there. And if it is, then it turns out that according to the reversing the chain rule, that the answer should be f of x plus a constant. So this method of U-substitution, basically U-substitution helps us to get from this situation to this situation. And so let's learn the steps. So let's go through the steps of the method of U-substitution, and we'll use the example from the previous slide. There are 5 steps. The first is to define u, because it's U-substitution. So u is going to be g of x, whatever the inside function is. And sometimes it's obvious, so the inside function is x squared because that's inside of cosine. Other times it's not so obvious, but we'll learn to deal with those situations. So we are going to define u to equals x squared. All right, and the next step is to differentiate, and that's to write du by dx, or find du by dx. So the derivative of u with respect to x is clearly 2x. And at this stage, we do something which feels slightly illegal, because we know du by dx is just, it stands for the derivative or the slope, but we're going to kind of cross multiply, take that dx onto the other side, and write in terms of differentials, du equals 2x dx. So what that means is that if you're interested in what the change in u is for any given change in x, the little change in u is going to be equal to 2x times whatever the tiny change in dx is. So you don't really have to kind of understand it. You just have to, at this point, just understand the algebraic manipulation. So step 3 is to substitute. And this is where we take our integral and we transform everything into terms of u. So I like to call this like we're moving from x land to u land. So, and to do that, I'm also going to rearrange it slightly, and you'll see why. So I'm going to take the 2x and move it after the cosine, because I'm hoping then that you'll see some sort of logical substitutions. So we know that x squared, we can replace x squared with u. And then we have this 2x dx here. But look where else we have 2x dx. So that can just be replaced with du. How convenient. So times du, but you don't even need that times there. It's sort of, you've got the integral in terms of u. So the next step is to integrate. And that's recognizing now we're at a simple situation where we have cosine of u du. That's no different from before when I asked for the integral of cosine of x dx. We can do something like that. So you need to see a very simple function in terms of u. So I've called that here little hu. And once you've got a very simple function like that, you should know the antiderivative. I've used uppercase h there. So we take cosine u du, and we know that the antiderivative of that is just sine of u plus a constant. And then the last step is just to back substitute. So we're coming back from u land into x land now. And we know that, so sine of u, well, u was x squared. And we still have the plus c, and that's our final answer. And now a good tip here is to always check your answer by actually taking the derivative. So remember, if you do d by dx of this, you would get cosine x squared times 2x, and the c would disappear, and it gets us to the desired, the original integrand, which was 2x cosine x squared. So for our first practice problem, so we have to define u to be the inner function. Sometimes with e to the something or any exponential situation, people are unclear what the inner function is. Well, always think of it as whatever is done to x first. So if I plugged in a value of x, the first thing I'd have to do is multiply it by 5 and add 2. So that's the inside function. And whatever answer I got to there, then I would raise that. I would do e raised to that power. So the inside function is basically the exponent. Differentiate, du by dx equals 5. Cross multiply, du equals 5 dx. Substitute. So let's bring this up here. So e to the 5x plus 2, we know that we can replace 5x plus 2 with u. But then we have a little issue here because we only want to substitute for dx. And right now we have 5 dx up there. So what we can do now, so we have to be prepared to make these little tweaks depending on the scenario, is we could divide both sides by 5. So bring that 1/5 over here so that we have dx isolated. And with that dx isolated, we can make this substitution. So in place of dx, we put 1/5 du. So in terms of integrating, then let's just, you could bring the 1/5 outside if you liked, outside the integral, or you could leave it like this. So we know the antiderivative of something as simple as e to the u. It's just going to be 1/5 e to the u plus a constant. And then we just back substitute. So u, what was u to begin with? It was 5x plus 2 plus a constant. So that is our final answer. And of course, don't forget to check by taking the derivative of that and making sure, taking the derivative of this answer, and making sure we get back to the integrand, which is, in this case, e to the 5x plus 2. So for our next practice problem, so we need to define u to be the inner function g of x, and in terms again of finding g of x, always look for the more complicated of the expressions there. So we have x cubed plus 4 being raised to the 5th power. So x cubed plus 4 must be the inside function. And if you think about it, the derivative of x cubed is something along the line of x squared. And we see an x squared hanging out there. So we know this should work pretty well. Differentiate du by dx equals 3x squared. And isolate du temporarily. We may need to tweak this, don't forget. So substitute. So again, I'm going to rearrange the integrand a little to make the substitution easier. So x cubed plus 4, this whole thing here is just u to the 5th. And now we have x squared dx. So we have x squared dx. So we'd like to just get x squared dx alone. So let's just bring the 3 to the other side. So we get this, which will make a nice, easy substitution. So in place of x squared dx, we are going to put 1/3 du. And just integrate that. And like I said, you can always put the 1/3 outside. So we have 1/3 the integral of u to the 5th du. Now, if you do put it outside, you're going to sort of get and you think about the integral, you're going to have to make one little adjustment. So the integral of u to the 5th is u to the 6th, 1/6, plus a constant. So if you distribute that 1/3 in, you get 1/18 u to the 6th. Now you think you might get 1/3 c. Well, 1/3 c will just be another constant. We could call it d, but we could also just call it c again, just a new c. And then back substitute, so 1/18 and u to the 6th. Now u was x cubed plus 4 plus a constant, and that's our final answer. And once again, don't forget to take the derivative to make sure you get back to the desired integrand. So here's an example that might sort of give you pause for thought. Do we make u sine x or do we make u cosine x? Maybe if we separate it out a little bit, we can kind of think about it. It's just sine x times 1 over cosine x. Well, sine x is just not a function within, it is just what it is. It's not within another function, but cosine x is indeed. What is it in? What is the overarching function? The overarching function is 1 over x, the reciprocal function. If I was to change that to x minus 1 on the denominator, I would have a composite function, and similarly with 1 over cosine x. So it might be a little hard to see, but trust the process and you'll see it work out in the long run. We want to make u equal to cosine x. So if we differentiate, we get this. And let's just isolate du for the time being. Okay, so now we are going to make the substitution. So cosine x gets replaced with u. And sine x dx, okay, let's see. We want sine x dx, not negative sine x dx. So let's take that negative to the opposite side, sine x dx. And then we can replace this with negative du. So bringing that negative outside. So we are in u land right now. We're going to take care of that integral. So the integral of 1 over u is ln the absolute value of u plus c. And then we back substitute, so we end up with our answer in terms of x. So u was cosine x to begin with, and that's our final answer. So for the last problem, we're going to notch up the challenge. And the first challenge is that should we make u equal to x plus 1 or the square root of x plus 1, because that's still a function within a function. And yes, you could make u equal to x plus 1, and I challenge you to do that in your own time, and you'll get the same answer as I'm going to get, but I'm going to make it the square root of x plus 1 and see what happens. So that means du by dx is x plus 1 to the half. The derivative is half x plus 1 to the minus a half. So, and then I can just put that minus negative half exponent, I can put the radical down here. And if I isolate du, I get 1 over 2 square root of x plus 1 dx. So I actually I'm looking at this and I see square root of x plus 1 over that dx, and I see that it's actually, I've got it going on right here as well. So I'm going to rearrange the integral in a slightly different way. I'm going to separate 1 over square root of x plus 1 dx because I'm sensing a nice substitution. To do that, I do need to get the 2 up to here first. So 2 du equals 1 over the square root of x plus 1 dx. And now I can see that here, I can replace this whole thing here with 2 du. Oh, except there's one problem, is I've still got an x there. So that is interesting because usually it's just so easy to transform into u world, but somehow we have to express x in terms of u. Well, fear not, look over here. We can square both sides, get x plus 1, and then we can isolate x in terms of u. And then we can come down here and make that substitution. So we have u squared minus 1 times 2 du. And if we integrate that, let's bring the 2 outside, u squared minus 1 du. So that's 2. Let's see. If we integrate u squared, that's u to the third. We need a 1/3. So in front of that, minus u plus c. Remember, we can distribute the 2 and still call that 2 times c, just make it c again. And then we just have to back substitute. Well, u was the square root of x plus 1 cubed minus 2 times the square root of x plus 1. So you could leave it like that, or you could kind of transform everything into rational exponents, and then we're done. So well done for making it to the end of the video. Here are 3 problems involving U-substitution for you to try. If you put the answers in the comments, I'll be sure to let you know if you're correct. And please do subscribe to my channel, Ready to Derive, and check out some of my other videos. Thank you.